Welcome back to the deep dive. Today, we are walking straight into the fire. And when I say fire, I mean that specific kind of heat that rises up the back of your neck when you open a technical document, see an absolute wall of Greek mathematical symbols, and realize I have to manage the people who do this.
Oh, yeah, that is a very specific, very relatable kind of heat. I think we've all felt it.
It really is, because we're tackling the CPMAI certification materials today, specifically the sections that tend to make project managers just, break out in a cold sweat. We are opening up the black box of machine learning. And I'll be totally honest, when I first looked at the source material, the committee guides, the exam content outline, the supplemental docs, my very first thought was I signed up to manage schedules, stakeholders, and budgets. I did not sign up to debug a neural network or derive a backpropagation formula.
That is the universal reaction.
Yeah.
It really, truly is.
Yeah.
I mean, I've seen seasoned PMs who have managed global construction projects worth hundreds of millions of dollars just freeze up when they see terms like hyperparameter tuning or regularization. The instinct is either to run away screaming or, perhaps worse, to try and frantically memorize the math without understanding what it actually does or why it exists.
Exactly. And the sources we had today are interesting because if you read between the lines, they seem to be trying to talk us down from that panic ledge.
They absolutely are. The core message here, and if you take nothing else away from this hour, take this, is the mission of this deep dive. The CPMAI exam and the methodology itself is not trying to turn you into a data scientist. It isn't trying to make you the person writing the Python code. It wants to make you the person who can govern the person writing the code.
That's a crucial distinction. It's kind of like the difference between knowing how to assemble a combustion engine from scratch versus knowing how to drive the car. And more importantly, knowing when the mechanic is trying to overcharge you for a repair you don't actually need.
Or when the engine sounds like it's about to explode, right? That is the perfect analogy. The exam tests the why and the when. Why are we using this algorithm instead of that one? When does this model become too risky to deploy? If a data scientist tells you they need 3 weeks and, $10,000 in cloud compute credits to run a grid search, do you know if that's a legitimate request or just a massive waste of the project budget? That is what we are digging into today.
So we have a pretty heavy stack of documents today. We've got the official PM guidelines, the technical appendices on learning paradigms, and the risk management frameworks. We've distilled this down into 3 main buckets for you as you listen, just to keep it organized.
Right. 3 pillars. First, we're going to look at the 3 learning paradigms. This is the absolute foundation. If you get this wrong, you solve the wrong problem. Second, we move to the risk, specifically the monster known as overfitting and the method we use to fight it, regularization. And third, the process hyperparameters and tuning.
And just to set expectations for everyone listening, we aren't going to just sit here and recite definitions. We are going to tear these concepts apart to see how they actually break a project if you ignore them. We're going to look at this strictly through the lens of a project manager who wants to pass the exam and actually deliver value.
Let's do it. Dive right in.
Okay, let's start with segment 1, the 3 learning paradigms. This maps directly to phase I of the CPMAI cycle, which is business interest. The documents make a massive deal about framing the problem. And apparently, you just can't frame a problem if you don't understand the difference between how these machines learn.
Correct. This is where most AI projects fail before they even write a single line of code. I can't tell you how many times I've seen a stakeholder come into a meeting and say, we want AI to fix our churn problem. Great. But what kind of problem is that? Is it a prediction problem? Is it a pattern finding problem?
Right, because the answer dictates which paradigm you use.
Exactly. If you pick the wrong one, you're basically building a boat to drive on a highway. It's just not going to work.
Yeah. The first one on the list is supervised learning. And the sources call this the teacher model.
It's the most common paradigm in business today. If you look at, say, 90% of the AI value being generated in the enterprise right now, it's supervised learning. Think of it as a traditional classroom environment. You have a student, that's your algorithm, and you have a teacher. The teacher gives the student a test, but they also give the student the answer key.
The answer key being the labels, right?
Exactly. Labeled data is the primary fuel here. You don't just dump raw, messy data on the machine. You give it the input and the correct output. You say, here is an email, and here's the label spam. Here's a picture of a lung scan, and here's the label tumor. Here's a historical loan application, and here's the label defaulted.
So the machine's job isn't to be creative or invent anything new. Its job is just to figure out the underlying logic that connects the input to the label.
It's a mapping exercise, pure and simple. Input A leads to output B. It looks at 10,000 examples, finds the mathematical relationship or the function that connects them, and then, and this is the key part, you take away the answer key. You give it a brand new email it has never seen before, and you ask, what is this?
And if it learned correctly, it confidently says spam.
Bingo. That is supervised learning. It
Yeah.
is supervision because we, the humans, told it exactly what the right answer was during the training phase.
Now, within this supervised world, the outline splits it into two problem types: classification and regression. I feel like seasoned PMs probably know this, but it's really worth clarifying because the nuance deeply matters for the exam and for gathering business requirements.
All matters for the business metric, too. You measure success entirely differently for these two. Classification is exactly what it sounds like. You are putting things into distinct buckets, categories,
Classes.
like spam versus not spam, right? That is binary classification. Two outcomes, yes or no, pass or fail, default or repay. It's a toggle switch. But it can also be multi-class. Think about a self-driving car seeing an object in the road. It needs to decide, is this a pedestrian, a tree, a stop sign, or another car? Those are discrete categories.
Right, the answer isn't, oh, it's 40% tree, it has to pick a bucket to put it in.
Well, technically, the algorithm might output a probability score under the hood, like, I'm 90% sure this is a tree. But the final business decision is a strict categorization. It treats the world as a set of distinct types.
Contrast that with regression.
Regression predicts a continuous number, a value on a sliding scale. It's not a bucket, it's a specific point on a line.
Like predicting the price of a house.
Yes, exactly. If I ask the model, how much is this house worth? The answer isn't high or low. The answer is $452,000.50. Or predicting the exact temperature tomorrow at noon. Or predicting the precise dollar value of inventory we will need to order next month.
This distinction seems simple on the surface, but I can totally see how it trips people up in requirements gathering.
It happens all the time. If the stakeholder asks, will we sell more than 100 units next week? That is a classification problem. It's a yes or no. But if they ask, how many units exactly will we sell? That is a regression problem. As a PM, you have to force the stakeholder to be incredibly specific because that single distinction changes the entire family of algorithms you select.
That's a really great way to distinguish them. And looking at the algorithm list here in the notes, we have linear regression, logistic regression, support vector machines, decision trees, random forest, neural networks. That is just a massive wall of jargon. Does a CPMAI candidate need to know the actual math behind, say, a support vector machine?
You don't need to know the kernel trick math, no. You don't need to know how to calculate the optimal hyperplane in an n-dimensional space, but you absolutely need to know the characteristics and the trade-offs of these tools.
Give me an example of a trade-off a PM would need to manage there.
Okay, consider interpretability. If you are in a highly regulated industry, like banking or healthcare, and you need to legally explain why the model denied a customer a loan, you probably shouldn't use a massive, complex, black box neural network. Neural networks are incredibly powerful, but they are notoriously hard to explain to an auditor. You might want to push the team toward a decision tree or logistic regression because those are interpretable.
Right, you can actually trace the logic step by step. Like it denied the loan because income was below X and debt was above Y.
Exactly. The exam might give you a scenario that says you need high interpretability for a regulatory audit. If you choose a deep neural network from the multiple choice list, you fail the question. You need to pick the white box model. That's the level of technical awareness a PM needs. You're picking the tool based on the business constraint, not just the coolness factor of the algorithm.
Okay, that makes total sense. Moving to the second paradigm, unsupervised learning. The sources call this the explorer model.
This is the Wild West of data science. In supervised learning, we had a teacher and a clear answer key. In unsupervised learning, there is no teacher. There are no labels at all. We basically just drop the student in the middle of a foreign country and say, hey, figure out how this place works on your own.
So we're just feeding it raw data, no spam or not spam tags attached.
Correct. Massive amounts of raw data. And we are asking the algorithm to find structure. Find me patterns that I don't even know exist. We aren't telling it what to find. We're asking it what is actually there.
The big business application here is clustering, right?
Right. Let's say you're a PM at a massive retail giant. You have a database of 10 million transactions. You don't actually know who your types of customers are. You don't have a magical column in your database that says budget shopper or luxury buyer. You just have millions of receipts.
You just have the raw purchase history, timestamps, items.
Exactly. So you feed this into a clustering algorithm like k-means, and it just starts grouping people based on mathematical similarity. It looks at all the data points in space and says, hey, these 50,000 people behave very similarly to each other.
And it might come back and say, hey, there is a distinct group of people who always buy diapers, beer, and painkillers every single Friday night.
The classic tired parent cluster.
Excuse
Exactly.
me.
The machine doesn't know what that group is. It doesn't have the human-labeled tired parent. It just knows these data points sit very close together in mathematical space. It's up to the human PM or marketer to look at that cluster and say, oh, that's a new market segment. Let's target them with a specific ad campaign.
So supervised predicts known outcomes, whereas unsupervised discovers unknown groups.
Perfect summary. Keep that in your back pocket for the exam.
The sources also mention dimensionality reduction here. This one always sounds a bit like sci-fi to me, reducing dimensions. It sounds like something from a Marvel movie where they shrink down to the quantum realm.
It does sound insanely complex, but for a project manager, it really just comes down to efficiency and budget. Imagine you have a spreadsheet with 5,000 columns. 5,000 unique variables for every single customer. Age, zip code, shoe size, last click time, mouse movement speed, eye color. It's just way too much noise.
And I imagine trying to process 5,000 columns for 1 million customers takes a terrifying amount of computing power.
It totally chokes the model. Data scientists call this the curse of dimensionality. The data is so sparse and spread out across so many variables that the model simply can't learn anything useful. So dimensionality reduction techniques like PCA principal component analysis do the math on the data and compress it.
So it just deletes the useless columns.
Not exactly deletes, it combines them. It finds deep correlations. It says, you know what? Income and average monthly spending are so closely related that we don't need both. Let's mathematically combine them into a single new variable called financial status. It distills the essence of the data. It's kind of like turning a massive, uncompressed raw video file into a streamlined MP4. It's the same movie. It's a smaller file. It's much easier to stream, but you do lose a tiny, tiny bit of granular detail.
That's a vital tool for the data understanding phase then. If your cloud compute costs are absolutely exploding, asking your data scientist, hey, can we use PCA here, makes you look like a genius.
It makes you look like a PM who deeply cares about the budget and the schedule, which is exactly what you're supposed to be doing.
And the third type under unsupervised is anomaly detection.
Finding the needle in the haystack. Or, more accurately, finding the hacker in the server logs.
This is huge for cybersecurity, right?
It's the primary use case. Think about credit card fraud. Most transactions are totally legit. Fraud is incredibly rare. You teach the model what normal spending looks like. You don't necessarily show it examples of attacks because you might not even know what a brand new attack looks like yet. You just show it normal.
You establish a baseline of behavior.
Right. Then, the second something deviates from that baseline, an anomaly, it flags it. So this user usually spends $50 at the grocery store in Ohio. Suddenly, 30 seconds later, they spent $5,000 at an electronics store in Lagos. That is a massive mathematical anomaly. The system flags it.
So if a stakeholder says, tell me what's in my data, use unsupervised. If they say, predict this specific outcome we've seen before, use supervised.
Precisely.
Yeah.
That is the phase-I framing you need to master.
Now the third paradigm, this is a cool one, reinforcement learning, the agent model.
This is totally different from the first two. Supervised and unsupervised are about learning from a static pile of history, a fixed database. Reinforcement learning, or RL, is about learning by doing. It's highly dynamic. It happens in real time, or at least in a simulation of real time.
The analogy the outline uses here is training a dog.
It really is the best way to think about it. You have an agent that's the AI. It exists in an environment. And it takes actions. Every single time it takes an action, the environment gives it immediate feedback, either a reward or a punishment.
Like, good robot, here's plus 10 points. Or bad robot, you hit a wall, minus 50 points.
Exactly. The agent's entire goal in life is to maximize its cumulative reward over time. It's trying to learn what we call a policy. A policy is just a strategy of which actions to take in which specific situations to get the absolute most treats possible.
And this introduces that famous trade-off I always hear about in RL, exploration versus exploitation.
This is honestly a life philosophy, not just an algorithm. Imagine you move to a new city and you find a restaurant you really like. That's a reward. Good food. Do you just keep going back to that exact same restaurant every single night?
I mean, that would be the safe bet. You know what you're getting.
That is exploitation.
Yeah.
You are maximizing your known rewards. You know for a fact you'll get a solid 7 out of 10 meal. But what if the new restaurant across the street is a 10 out of 10? You'll literally never know if you don't try it.
But if I try it, it might be a 1 out of 10. I might get food poisoning and lose the evening.
That is exploration. You actively accept the risk of a short-term punishment, a bad meal, for the potential of a long-term higher reward, finding a better regular spot. The RL agent has to balance this math perfectly. It needs to explore enough to map out the environment, but exploit enough to actually rack up the high score.
Where does a PM actually see this in the real enterprise world? Because I don't see a lot of local banks using reinforcement learning to approve stand-up mortgages.
You won't. You really won't. RL is incredibly computationally heavy, very hard to stabilize, and notoriously difficult to implement for simple business logic. You see it in robotics, literally teaching a Boston Dynamics robot how to walk over rubble. You see it in massive warehouse automation systems. You see it in self-driving cars because navigating a constantly changing physical road is just a continuous series of split-second decisions.
And sometimes in things like dynamic pricing for airlines or automated stock trading.
Yes, high-frequency trading agents are often RL-based. They buy, they sell, they see if they made money, which is the reward, or lost money, the punishment, and they adjust their trading strategy on the fly. If your project involves a system that has to make a continuous sequence of decisions in a constantly changing environment, that's RL.
Okay. So we have our what? Supervise is the teacher, unsupervised is the explorer, reinforcement is the agent. That properly frames the problem for phase I. But even if we pick the perfectly correct paradigm, the sources scream about a specific terrifying risk, a risk that can completely kill a project right after launch: overfitting.
Overfitting is the silent killer of AI projects. It is hands down the #1 reason why machine learning projects look perfectly green on the PM status report, but burn red on the balance sheet once they go live.
Let's move right into segment 2, overfitting and regularization, because this is where the rubber meets the road for quality assurance and testing.
It really is. And to understand overfitting, we have to go all the way back to our student in the classroom analogy.
Let's define it. The source uses the memorization analogy again, right?
Yeah, imagine a student who is preparing for a massive final history exam. But instead of actually studying the deep causes of the war or the broad themes of the era, they just aggressively memorize the practice test the teacher handed out. They memorize every single specific question and every single specific answer on that one sheet of paper.
So they can just recite it back perfectly, word for word.
They get a flawless 100% on the practice test. The PM looks at that metric and says, wow, the model is 100% accurate. We are ready for production. Ship it.
But then the student walks into the real exam room.
And the real exam asks a question that is phrased just slightly differently. Or it asks about a date that was a day off from what was on the practice sheet. The student completely freezes. They fail the test completely.
Okay, why does that happen?
Because they didn't actually learn the underlying concept. They didn't learn the pattern. They just memorized the noise of that specific practice test.
So in technical terms, the model learned the training data so well, so precisely, that it picked up on the random fluctuations, the data entry errors, the absolute weirdest outliers.
Correct. Real-world business data is incredibly messy. It has a ton of noise. Training data is just a tiny, limited snapshot of the real world. If you fit your model to that snapshot too perfectly, you completely lose the ability to generalize to new data. And trustworthy AI, which is a huge, huge part of the CPMAI framework, is all about generalization. If your model doesn't work on brand new data it hasn't seen before, it's practically useless to the business.
So what actually causes this? Is it just bad, dirty data?
It can definitely be bad data, but more often than not, it's a problem of model complexity.
Too much algorithmic horsepower.
Exactly. If you use a model that is way too powerful, like a massive deep neural network with millions of parameters for a very simple problem, it has so much memory capacity that it just records the data instead of learning from it. It's like using a massive supercomputer to do simple addition. It overthinks it. It starts finding weird patterns that aren't actually there.
Give me an example of a fake pattern. Like, what does that look like in practice?
Imagine you're trying to build a model to predict stock prices. You feed the model way too many features. You give it everything. The model notices that in your specific training data, every single time it rained on a Tuesday when the stock market was up, a specific customer in Ohio bought a green hat.
I mean, that just sounds like a random coincidence.
To a human, it's obviously a random coincidence, but to a complex mathematical model that is desperate to reduce its error rate to 0, it looks like an absolute ironclad rule. Rain plus Tuesday equals green hat purchase. It memorizes that rule.
Yeah.
Then you launch the model into production, it rains on a Tuesday, and the model confidently predicts a hat purchase. The purchase doesn't happen. The model fails. That is overfitting in a nutshell.
So the main causes are model complexity, small data sets, because it's way easier to memorize a short book than a long one, and irrelevant features which act as noise.
Exactly, you nailed it.
So how do we actually stop it? Because as a PM, I need a mitigation strategy. The outline points us to a concept called regularization.
Regularization is the antidote to overfitting. If overfitting is the model running wild and trying to be way too complex and clever, regularization is a set of heavy handcuffs.
I kind of love the idea of handcuffing the AI. How does it work mathematically, though, without getting too deep into the weeds?
We add what's called a penalty term to the loss function.
Okay, let's unpack that. What exactly is a loss function?
The loss function is basically the scoreboard for the algorithm. It's how the model measures its own error during training. Normally, the model just wants to minimize error at all costs. It wants a perfect zero score. With regularization, we change the fundamental rules of the game. We tell the model, you need to minimize error, but every single time you add complexity, every time you give a feature a huge mathematical weight, I am going to add a penalty score to your final result.
So the model is forced to make a constant trade-off.
Exactly. It has to look at every feature and decide, is this extra bit of complexity actually worth the penalty I'm going to take? If a feature is really, really predictive and important, it's totally worth the penalty. But if it's just noise, like our rain on Tuesday example, it's not worth the penalty at all, so the model just ignores it.
It effectively forces the model to keep things simple.
Right.
It's basically Occam's razor for AI.
Beautifully put. Occam's razor. The simplest explanation is usually the correct one. Regularization forces the mathematical model to find the simplest possible pattern.
The CPMAI materials highlight two specific types of regularization that always seem to appear on the exam, L1 and L2. L1 is lasso, L2 is ridge. What's the practical difference for a project manager overseeing this?
Think of L1 lasso as a laser scalpel. It has a very unique and very aggressive mathematical property. It can shrink the importance of a feature all the way down to absolute zero.
Zero. So it effectively just deletes the feature from the model.
Yes. It performs what data scientists call feature selection. If you have a massive data set with a lot of garbage variables, lots of noise, lots of irrelevant columns, L1 regularization will look at them, realize they add no real predictive value compared to the heavy penalty, and just zero them out completely. It cleans up your model and makes it sparse.
So if I know my project's data is super messy and has lots of irrelevant columns, I should be asking my lead data scientist if they're using Lasso.
It's a fantastic question to ask in a status meeting. Hey, we have 10,000 columns here, and I bet half of them are junk from legacy systems.
Yeah.
Should we try L1 regularization to prune this down? That is a textbook phase 4 model development conversation.
Now, what about L2, ridge regularization?
L2 is very different. It's much more like a dimmer switch than a scalpel. It shrinks the coefficients, the importance weights of the features, towards zero, but it rarely ever actually hits zero. It keeps all the features in the model, but it severely limits their extreme influence.
So it prevents any single feature from screaming too loud and dominating the prediction.
Exactly. It handles what we call collinearity, which is when multiple features are highly correlated with each other very well. It spreads the credit around evenly. It ensures that the model doesn't rely too heavily on any one single piece of data, which makes the whole thing much more robust.
So just to summarize for my own sanity, L1 cuts and L2 smooths.
That is the perfect cheat sheet definition for the exam.
Yeah.
L1 cuts features out, L2 smooths them down.
And as a PM, where do I actually see this happening? This is all in phase 4, right?
The literal coding and implementation happen in Phase V, model development. That's when the data scientists are in the trenches writing Python. But the validation happens in Phase V, model evaluation. And this is a crucial distinction for this CPMAI exam.
How do I practically check for overfitting in phase V? What report am I looking at?
You look at the performance gap. You ask the team to compare the model's accuracy on the training set versus the validation set.
So if the training score is, say, 99% and the validation score is 98%.
That's a massive win. It's generalizing beautifully. You're ready to move forward.
But if the training score is 99% and the validation score drops to like 70%?
Then you have a severe overfitting problem. The student memorized a practice test but completely failed the real one. That gap is your glaring red flag as a PM. And your immediate next question to the team is, guys, are we overfitting? And what is our regularization strategy to fix this?
You don't jump in and fix the code yourself. You flag the risk and manage the solution. That is the core CPMAI way.
Precisely. Oversight, not engineering.
Okay, let's take a breath. We've picked our learning paradigm in Phase I. We've successfully handcuffed the model with regularization to stop it from cheating in Phase 4 V&V. Now, we need to fine-tune the whole system to get the best performance. This brings us to segment 3, hyperparameters and tuning.
This section is essentially a vocabulary test that trips up so many people. There are parameters and there are hyperparameters. They sound almost exactly the same, but they're absolutely fundamentally not the same thing.
Let's cleanly distinguish them for the listener. Parameters are internal, right?
Yes. Model parameters are the things the model learns completely by itself during training. The internal weights, the biases, the specific split points in a decision tree. The human data scientist does not manually set these. The data sets these. That's literally the definition of machine learning. The machine is learning its own parameters.
So then what on earth is a hyperparameter?
Hyperparameters are the configuration settings that the human chooses before the learning even begins. They are the external dials and knobs on the machine itself.
The outline uses the oven analogy here, and I really like that one.
It's the best way to visualize it. If you are baking a cake, the internal chemistry of the batter rising, the proteins denaturing, the sugar caramelizing, that's the internal process. That's the model parameters. You don't control that once it's in. But you, the baker, have to set the temperature to 350 degrees and the timer to 45 minutes before you close the door.
Right, the oven doesn't decide its own temperature, I do.
Exactly. Those external settings, the temperature and the time, are the hyperparameters.
In the context of AI, what are these dials? What are we actually setting before we hit run?
Things like the learning rate.
What is that?
That dial controls how fast the model updates its internal beliefs when it sees an error. If you set the learning rate too high, the model jumps to wild conclusions. It overshoots the correct answer entirely. But if you set it too low, it crawls. It takes 1,000 years of compute time to learn anything useful.
So it's basically a speed dial.
Right. Other examples include the number of trees in a random forest algorithm. Do you want 50 trees or 500? Or the K in K-means clustering, exactly how many clusters do we want the model to try and find? Or the number of hidden layers in a deep neural network. These are all architectural, structural decisions made by humans before the training phase starts.
So getting these hyperparameters wrong can completely ruin the model.
Absolutely. You set the oven to 600 degrees, you burn the cake to a crisp. If you set the learning rate too high, the model's math explodes and it never converges on a solution.
So we have to tune them. Hyperparameter tuning, honestly, this sounds incredibly tedious.
It is easily the most tedious, mind-numbing part of the data science lifecycle. And for a project manager, it is often the most expensive part of the entire project.
Why expensive? Just human hours?
Human hours, yes, but mostly compute costs. Because tuning basically means running the entire model over and over and over again with slightly different settings until we miraculously find the best combination. Each run costs time. Each run costs massive compute power. If you are using expensive cloud GPUs on AWS or Azure, the meter is running the entire time.
That sounds like just setting the project budget on fire.
It can be. That's exactly why the method of tuning you choose matters so much. The outline lists 4 specific strategies. Let's run through them from a time versus cost perspective, because that's what the PM actually cares about.
First up on the list is manual search.
The old gut feeling method. The data scientist sits there, scratches their chin, and says, I think I'll try a learning rate of 0.01. They run it for 3 hours. Not good enough. Let's try 0.02.
Is that efficient at all?
It's terrible. It's almost impossible to reproduce. It relies entirely on luck, and it depends heavily on the seniority of the data scientist. A really senior person might have good intuition and guess right. A junior person is just throwing darts in the dark. You really want to avoid this for serious production systems.
Next is grid search. Now this one sounds organized and thorough.
Grid search is the brute force method. You explicitly define a grid of values. You say, okay, computer, I want you to try learning rate 0.1, 0.01, and 0.001. And I want you to try trees at 10, 50, and 100.
And the computer just methodically tries every single combination.
Every single possible intersection. It runs the entire model with 0.1 and 10, then 0.1 and 50, then 0.1 and 100, and so on until it finishes the grid.
That sounds incredibly thorough. It's basically guaranteed to find the best option.
Well, it guarantees you find the best setting within the specific grid you defined. But do the math on the scale. If you have 5 different hyperparameters and you want to test 10 options for each one, that is 10 to the power of 5. That is 100,000 full runs of the model.
Whoa.
Right. And if each run takes an hour to process on a massive data set, do you have 100,000 hours?
We'd miss our launch deadline by a decade.
Exactly. Or you completely bankrupt the IT department paying the cloud provider. Grid search is safe, it's thorough, but it is incredibly, prohibitively expensive as the model complexity grows.
So what's the realistic alternative? The next one is random search.
Random search sounds like a terrible, lazy idea, but it's actually brilliant in practice. Instead of checking every single strict intersection on a grid, the computer randomly selects combinations from the defined space to test.
How can random possibly be better than organized? It sounds like we're just gambling with the budget. It's highly probabilistic. It turns out that usually in high-dimensional hyperparameter space, only 1 or 2 of the dials actually matter significantly for the final performance. Grid search wastes a massive amount of time checking the unimportant dials over and over and over again in rigid steps. Random search explores the total space much more efficiently. Empirical research shows it often finds a model that is like 95% as good as grid search, but it does it in 10% of the time.
So if I'm a PM on a super tight deadline and I see scenario B in the outline,
You strongly advocate for random search. It's the good enough, fast option for when time is money.
but what if we want to be genuinely smart about it? What if we have the time and we need the absolute best possible performance for a high-stakes model? The outline mentions Bayesian optimization.
This is the absolute gold standard in modern machine learning. Bayesian optimization is actually smart. It learns from its own past attempts.
How does it do that? Think of it like a guy with a metal detector looking for gold on a massive beach. Grid search digs a hole strictly every 5 feet, regardless of what it finds. Random search just digs holes totally randomly across the beach. Bayesian search digs a hole, finds nothing, and mathematically updates its assumptions. It says, okay, the gold probably isn't in this sector. Let's move our efforts to that other area over there where the probability of finding a signal is much higher.
So it builds a model of the model.
Yes, exactly. It builds what we call a surrogate model. It uses complex probability to intelligently guess where the absolute best settings are hiding. It perfectly balances exploration checking entirely new areas of the settings and exploitation refining the areas that look really promising. It converges on the perfect settings much, much faster than grid search and is significantly more accurate than random search.
This is the ultimate work smarter, not harder approach to tuning.
Exactly. If your data science team comes to you asking for a massive GPU budget increase for tuning, you ask them, are we doing a brute force grid search or are we using Bayesian optimization? If they say Bayesian, you can probably approve the budget with confidence. They know what they are doing and they are being efficient.
There's one last method mentioned in the outline, evolutionary strategies.
This one is fascinating. It's biologically inspired. It's literally survival of the fittest for algorithms. You create a population of different hyperparameter settings. You test all of them. You kill off the bad ones that underperform. You take the winners. You breed them together by mathematically combining their settings. You add some random mutations, and you run it again. Over many, many generations, the hyperparameters evolve to be absolutely perfect for the problem.
That is wild. It sounds like science fiction.
It is wild.
Yeah.
It's highly effective for very complex, non-standard AI problems. But again, it requires running many generations, so it is still computationally expensive compared to basic random search.
And bringing this all the way back to the PM life cycle and the exam, this planning, deciding which tuning method to use, this happens in phase 3, algorithmic approach, right?
Yes, exactly. Phase 3 is where you sit down and do your tooling and infrastructure planning. This is the moment where you decide as a team, do we actually have the hardware budget for an exhaustive grid search? Or do we need to stick to random search to hit our Q3 deadline? The technical decision on how to tune directly drives the project schedule and the financial budget.
I really love that connection. It deeply reinforces the core mission of this deep dive. We don't need to do the Bayesian math ourselves, but we absolutely need to understand the schedule and cost implications of the math.
The cost, the timeline, and the risk.
Yeah.
That is exclusively the PM's domain. Let the data scientists do the math. You manage the impact.
So let's start to wrap this up. We've covered a truly massive amount of ground today. My head is spinning a little bit, but in a really good, productive way.
Let's anchor it all down. If you are a PM preparing for the CPMAI exam right now, or even if you're just trying to survive your next planning meeting with a data science team, let's visualize a mental cheat sheet.
Perfect. Let's build the summary table.
Okay. Row 1, The paradigms. If we are predicting specific labels from history, what is it? Supervised. If we are discovering hidden patterns in raw, messy data, unsupervised. If we are navigating an environment using real-time rewards and punishments, reinforcement.
Got it. Phase I problem framing is locked in.
Row 2, the risk. The model works perfectly in the lab but completely fails in the field because it just memorized the noise of the training data. That is overfitting. And what is the fix? Regularization. L1 lasso to cut useless features out entirely, L2 ridge to smooth their influence down.
Check. Phase VI and V risk management.
Row 3, the process. We need to set the external dials before we bake the algorithmic cake. Those are hyperparameters. Don't let your team waste precious money on manual search or massive grid searches if you can avoid it. Push for random search if you're in a hurry on a tight budget, or Bayesian optimization if you want the absolute best results efficiently.
And remembering how that maps to the phases. Phase I for picking the paradigm. Phase 4 and V for coding and evaluating regularization. Phase 3 for planning the tooling and infrastructure budget for tuning.
Exactly. It's all about mapping the deeply technical concepts directly back to the project management lifecycle.
You know, reading through the very end of the source material today, there was a conceptual question that really stuck with me. We spent all this time talking about the machine learning from the data and us tuning the dials on the machine to make it learn better. But it really begs a bigger question. Who governs the tuner?
That is the ultimate question of trustworthy AI. And honestly, it's the entire reason the CPMAI certification even exists. The algorithm itself is completely amoral. It doesn't have ethics. It just relentlessly optimizes the math you give it. If you tell an AI recruitment tool to maximize the probability of a successful hire, and it notices in the historical data that historically, men were hired and promoted more often than women.
It will just overfit to that exact bias. It will learn that discriminatory pattern as a rule.
Exactly. It will tune itself to quietly reject female applicants. Not because the AI is inherently evil or prejudiced, but because that's exactly what the historical data, the flawed answer key we provided, taught it to do.
The machine did exactly what you told it to do. It optimized the reward function based on bad data.
Correct. The tuner, the project manager overseeing the system, is the one who has to stand there in the room and say, wait a minute, this metric is fundamentally flawed. This historical data is biased. This model result, while mathematically optimal according to the loss function, is ethically and legally unacceptable for our business.
The PM is essentially the conscience of the AI project.
You are the ultimate guardrail. You are the vital bridge between the raw, cold math and the actual human business value. If you check out mentally during phase 3 or phase 3 just because the math looks too hard on the whiteboard, you are completely abdicating that critical responsibility.
That is an incredibly powerful place to leave it today. For everyone listening, don't be intimidated by the black box of machine learning. Your job isn't to build the box from scratch. It's to understand how it works well enough to make sure the box doesn't accidentally destroy the business or hurt your customers.
Or make automated decisions that we as an organization simply cannot stand behind in public.
Exactly. Thank you so much for breaking all of this down. It genuinely feels a lot less like a terrifying black box now and more like a manageable process.
My absolute pleasure. It's complex stuff, but it's totally manageable once you see the framework. Good luck to everyone out there with the exam preparation.
We'll catch you on the next deep dive. Keep learning, keep pushing.
And always keep questioning the data.
Bye for now.